everyone. Today we're going to do a little bit of a review of Hess's Law and then talk through an example of one of these problems. So Hess's Law is made up of three rules. The first rule is that if a reaction is multiplied by a factor, then the delta H value, which remember is a numerical value, is also multiplied by that same factor. So what that means is if we have a reaction like this, so I'm writing A plus 2B yields C, that reaction has some enthalpy value, so a delta H value. And then let's say we multiply that entire reaction by 2 to get 2A plus 4B yields 2C. So this new reaction is also going to have a delta H value. And that delta H value is going to be equal to 2 times delta H 1. So that's the first rule. The second rule is that if an equation is reversed, so let's say we have that same equation to start with the same enthalpy value, and we decide to reverse that equation to get C decomposing to A plus 2B, then that's also going to have a delta H2 value, so some other delta H value. And in this case, it's going to be equal to the opposite of delta H1. And this is important because this is what Hess's law really is. And this is that if we have a chemical reaction that is made up of multiple smaller steps, so different individual reactions, we can add those individual reactions together to get to our main reaction, the one that we were looking at. And that means that we can also add our delta H values together. So here's what I mean. If we're starting with our A plus 2B yields C, and we have another reaction that C goes on to react to form 2D, if we were to add these two reactions together, the C's are going to cancel because we have one on the reactants and one on the product side, and we're going to get a new reaction, A plus 2B yields 2D. So we know that our first reaction has a delta H value. Our second reaction has its own delta H value. So since we added those two reactions together, our new reaction is going to have also its own delta H value, and that delta H value is going to be the sum of the other two. Just like we added the reactions together, we can add together those numbers. And here's how that actually works from the standpoint of an actual chemical reaction. So imagine we have this chemical reaction. So we have solid carbon, gaseous H2O. When those are added together to react, they're going to yield carbon monoxide in the gaseous form and hydrogen gas. And let's say that we want to figure out what our delta H of this reaction is. So we don't know that value, but there are some other reactions that we do know. And from the point of view of a student who's actually working through these problems, these other reactions would be given to you either in a table or in the appendix of a textbook, something along those lines. So let's say that we have, this is our first reaction, carbon plus O2 gas yields CO2 gas, and that has a delta H of negative 393.5 kilojoules. We have a second reaction, 2CO gas plus O2 gas yields 2 CO2 gas. And the delta H value for that reaction is negative 566.0 kilojoules. And we have a third reaction, and that is 2H2 gas plus O2 gas yields 2H2O. And that has its own delta H value, which is negative 483.6 kilojoules. So what we're trying to do here is we're trying to combine these three reactions in a way that is going to give us the top reaction. So that means that all of our products and reactants have to be on the correct side, and we don't want to end up with anything that wasn't in our original chemical equation. So that means that we don't want to end up with any O2, and we don't want to end up with any CO2. So here's how we do that. First, we know we want to end up with carbon as one of our reactants. So we can already get that just by using this first reaction. So this first reaction is going to remain unchanged. So because that remains unchanged, our delta H value also remains unchanged. So our delta H value for that reaction is still negative 393.5 kilojoules. So in our second reaction, we know that we have some CO, we have some oxygen that we don't want there, and we have some CO2 that we don't want there. So it's not really clear yet what we are going to do with that CO2, but we know that we want the CO to be on the other side. So what we can do is we can flip that entire reaction. So if we flip that entire reaction, then we're going to get 2 CO2 yields 2 CO plus O2 gas. And since we flipped that reaction, that means that we're going to have to change the sign. So something else that we're going to have to do, now you can see that we could cancel one of these COs with one of these COs, but we're still left with an extra, CO2s with that CO2. We're still left with an extra CO2, and we have an extra CO there that we don't necessarily want. So the next thing we're going to have to do to that same equation is we're going to have to multiply by 1/2. So not only did we flip it, we're also going to have to multiply that equation by 1/2, which is the same as dividing by 2. So just going to erase those for clarity. So if we're dividing that entire reaction by 2, which is the same as multiplying by 1/2, then we're going to get CO2 gas yields CO gas plus 1/2 O2 gas. And because we also had to multiply it by 1/2, that means we have to multiply our delta H value by 1/2, and that's going to be positive 283.0 kilojoules. Remember that we changed the original from negative to positive when we flipped the equation. And again, just for clarity, now I'm going to get rid of that one. So this is now our new version of 1 and our new version of 2. So now we have to figure out what we're doing with reaction 3. So at this point, we have our H2 on the wrong side, so that means we're going to need to flip it. And we also have 2 of them instead of 1, which means that we're going to have to multiply by 1/2, just like we did with the previous one. So I'm going to do all of that in one step. And when I flip that equation and multiply it by 1/2, that's going to give us that's going to give us H2O gas. Sorry, I forgot our gas sign over there. Yields H2 gas plus 1/2 O2 gas. And since we flipped that and multiplied by 1/2, that means we're also going to do the same thing with our delta H. So we are going to change the sign from negative to positive, and we're going to multiply it by 1/2, which is going to give us 241.8 kilojoules. So now we're going to want to check our work. So to check our work, we're going to add these reactions together. So we're going to get carbon plus oxygen. So those are the reactants from reaction 1. And now we're going to do the reactants from reaction 2. So plus CO2, and then the reactant from reaction 3, which is H2O. And then that is going to yield the products. So here are the products we're going to include. CO2 plus CO plus H2 plus O2. So what I did here with the O2 was, because there are 2 of them here, both multiplied by the factor of 1/2, I just added 1/2 H2O plus 1/2 H2O is equal to 1 whole H2O. Or sorry, not H2O, O2. So half an O2 plus half an O2 equals 1 whole O2. So now we can actually cancel from one side to the other. We know that we don't want any of that O2 there, and there's 1 on each side, so we can cancel those. There's also a CO2 on each side, so we can cancel those as well. And then we can see what we are left with, and we are left with CS plus H2O yields CO plus H2. That is the same as the reaction we started with up at the top. So we know that we manipulated these reactions correctly, because when we added them together, we got what we were trying to get. So now what we can do is we can add those delta H values together. So we can add our first one plus our second one plus our third one. So we get delta H1 plus delta H2 plus delta H3. So when you add together those 3 values that I just highlighted, you are going to get positive 131.3 kilojoules. And that's how you solve the Hess's Law problem.